Today is Sunday, January 8th, 2012. This is a video showing a new improvement to a device to convert wind into usable electrical energy.
Is that orange juice for me, Mom?
Now, you can see down here there's a piece of fabric and a fan behind it forcing air through across the fabric, and the fabric is exhibiting aerodynamic flutter, a well-known phenomenon. However, the fabric is pinched along the sides of both ends. If I pinch at the back and pull taut, the aerodynamic flutter virtually disappears. So the magnitude of the flutter and the existence of the unstable oscillation causing the flutter is damped by tension along the entire side of the strip. All right? So, with that in mind, there are two patent disclosures that I'd like to identify because they show a scope of enablement for related inventions. The first one is International Patent Application Publication WO2008151008. This is by the inventor Sean Fain, and the entire disclosure of this publication provides various mechanisms for converting vibrations in a sheet of material constrained at the ends, like the one shown below, into mechanical or useful energy, mechanical or electrical energy. Another more recent publication is U.S. Patent Application Publication 2009 0285668 by the inventor David Lebrecu, which discloses a mechanism to convert wind energy into useful mechanical energy by using a fixed wing sail anchored by a weight that rotates around in space, and the end of which pulls back and forth to move a magnet or light to convert mechanical energy into electrical energy. Now, with those two background disclosures in mind, the first improvement on those systems, or a different invention that also converts wind energy into useful mechanical power, is, move away, Benjamin, this wing structure. Now, what this is a sheet of fabric, in this case ripstop nylon. Are you still recording?
I don't know how to make it.
Ripstop nylon, which is constrained by a rope along the front end at two endpoints, bottom and top. And you'll notice that the ripstop nylon, which is approximately 5 feet long, just under 2 meters long, executes an oscillatory vibration of significant magnitude. And this is a single mode vibration where the endpoints are stopped, and this ripstop nylon is oscillating at what's considered to be the fundamental mode between two endpoints, executing a single frequency oscillation in the plane generally perpendicular to the flow field of the air. In this case, you'll see there's 3 box fans all spinning at the lowest setting, providing a semi-uniform flow of air.
4 box fans.
4 box fans. And the sail is executing this oscillatory motion. It's relatively easy to convert oscillatory motion like this into electrical power, and I'll show that shortly by noting that the bottom of this, the bottom string is actually constrained to the floor. Between the floor and the sail there is a spring, and above the spring there are magnets constrained in place. The magnets are inside a magnet coil here. If I connect the magnet coil to this oscilloscope, you'll see that the oscillation of the magnet inside the coil results, as one would expect, in significant electrical power conversion. Get this clip on. There we go. So now you can see the conversion, and if I stretch this magnet back so the magnet is at the at or near the tip or top of the coil, you get a very large induced EMF, as is well known in the art. And the frequency changes because I've increased the tension on the rope, so the frequency went up a little bit. Right, so these vibrations now are on the next scale up. Vertical gain. There we go. And this is this signal is being synced externally to the vibration. The sync is shown here across to the external sync input. So this just shows that you can convert this type of oscillatory motion into electrical energy by converting the mechanical energy, movement of the magnet, into useful energy, useful electrical energy. This is a very simple display. There's many other types of mechanisms to convert the mechanical energy into useful electrical energy, several of which are shown in the Shane W.O. publication I quoted earlier. However, an issue with this type of invention is that although this structure is shown oscillating at fundamental mode and the wing is approximately 5 feet long, there is a question of whether this scales because, as it's well known, there are other modes of vibration. We're exciting one mode of vibration. With that in mind, let's step outside to view a wing which is 10 feet long, and I'll show how that wing is constrained to oscillate in the fundamental mode, which is a significant advance because it provides for scaling of this type of structure to very large, very long wings, and therefore very high power conversion. So with that in mind, let's step outside, turn these fans off. Now, the concepts behind these inventions have not been disclosed outside of confidence. What I'm going to show you in the front yard of our house is an example of a wing in which the higher order modes have been suppressed, and that's the critical feature for scaling, so that the wing or sail or flexible membrane oscillates in the fundamental mode and can be converted easily into useful energy. So what you see here is a long extended pole, approximately 12 feet. There's a 10-foot sail, again made of ripstop nylon, approximately 12 millimeters in depth in direction perpendicular to the pole, and 10 feet in length along the direction of the pole. Now, a critical feature of this structure is, first of all, again, there's a cord running along the front edge of the wing that's used to constrain the wing and maintain basically a section of material that cannot be extended, has a very high tensile resistance, tensile strength compared to the flat area of the fabric. And therefore the fabric can deform, whereas the front edge of the wing will not deform. It will not change its length along the direction of the pole to any substantial degree. However, if this sail is oscillated in the wind without any other changes, many modes are generated, and the fours at the end of the sail along the string or rope would oscillate at a corresponding series of mixed up frequencies and not provide for a large swing back and forth in fundamental mode, or a large oscillating tension along the direction of the string in a fundamental mode, and therefore not provide a very useful mechanism or effect to be converted to mechanical or electrical energy. However, in this sail, or this wing, I've constrained the back side of the sail by putting little kinks in it, folds, that create a tension on the back side of the sail that effectively couple locations along the sail together to maintain a curvature in one direction, either this way, curved down, look over my hand is, curved down all along the wing, or this way, curved up all along the wing. A consequence of that constraint is a filter out of the higher frequency modes because it forces all of the sail to be along the same curvature, which is fundamental to the base oscillation of the fundamental mode. In this case, the fundamental mode has a oscillation, whereas any point along the front edge of the wing executes a deformed figure 8, as shown as follows. This, like that, like that, like that. Because of the forces on the wing, that's the type of motion it generates. The result is a very large deformation in the direction perpendicular to the wind flow, and a smaller deformation in the direction back and forth with the wind flow. You'll see that in a second as I take this device, tension the front end, and twirl it.
Twirl it away from the house.
Oops, stop the film, I have to make it